Greeting everyone. Today our group will be presenting about quantum computing. The reference paper that we use are from Ishita Ray, published in 2011. Here is our group member including me, Pattaraphum Chuamuangphan, and my friend Muhammud Binhar. Okay, so the first topic is introduction. The researcher realized that in the last 2 decades of the 20th century, the standard model of computation placed limit on computation, which led to making a research applying a quantum mechanics instead of using classical computational by placing a computation on a quantum mechanical foundation. Faster algorithm is make a researcher found about novel cryptographic mechanism and alternative method of communication of quantum. Quantum computing is a field of quantum information processing that lead to change not only in the physical process used for computation and communication, but the very notion of information and computation themselves. In quantum computer, we exploit quantum effect to compute in ways that are faster or more efficient than, or even impossible on convenient computer. Which means that quantum computing does not provide efficiently solution to all problems. And also, quantum computation enables certain problems to be solved efficiently, whereas some problems which on a classical computer would take more than the age of the universe, while a quantum computer could solve in a couple of days. On the other hand, for other problems, it has been proven that quantum computation is improved a little bit or even cannot improve on classical method. Okay, so next is a quantum computing element. The topic in this section are including bit and qubit, entanglement state, and quantum circuit. For bit and qubit, in quantum mechanical system, the model can be represented by two-dimensional complex vector space, which can be viewed as a qubit. For example of such a system including photon polarization, electron spin, and the ground and excited state of the atom. A key difference between classical and quantum system is the way in which component system combine. The state of a classical system can be completely characterized by the state of each of its component pieces, which are 0 and 1, but aspect of the quantum system is not the most state cannot be described in terms of the state of the system component until we measurement on the qubit. For example, of the state cannot be described in terms of the state of the system component are state called entanglement state. Another important property of quantum system is a quantum measurement. Despite there being a quantum of possible state, any measurement of system of a qubit has only a discrete set of possible outcomes. For n qubit, there are at most 2 to the power of n possible outcomes. After measurement, the system will be one of the possible outcome state. Thus, the outcome obtained from a quantum measurement is a probabilistic, which is the most probability of the state will be the outcome. By doing quantum measurement, we are disturb the quantum state, so this will change the original state of quantum. A qubit has 2 arbitrarily chosen distinguished states labeled by K0 and K1, which are the possible outcomes of single measurement. Every single qubit state can be represented as a linear combination or superposition of these 2 states. In quantum information processing, classical bit values of 0 and 1 are encoding into the distinguished state by K0 and K1 in quantum. From encoding enable a direction comparison between a bit and qubit. So, in bit can only take on 2 values, 0 and 1, while qubit can take on any superposition of this value, such as A K0 plus B K1. Okay, so next is entanglement state. Entanglement state is a phenomenon where 2 or more particles become connected in such a way that their properties are correlated, regardless of the distance between them. This means that if one particle is measured, the state of the other particles is immediately affected, even if they are far apart. This property of entanglement can be useful for computational purposes. In quantum computing, measuring entangled state allows for the correlation between the particles to be accounted for, which can lead to faster and more efficient algorithms. Next is quantum circuit. If we take a quantum state, represent one or more qubits, and apply a sequence of unitary operation, which is a quantum gate, the result is a quantum circuit. We now take a register and let gate act on a qubit, in analogy to a conventional circuit, like a figure on the left side. The circuit is a series of operations and measurements on the state of n qubit. Each operation is a unitary and can be described by an 2 to the power of n multiple by 2 to the power of n matrix. Each of the line is an abstract Y. The box that contain the UN are quantum logic gate, which is a series of gates, and the meter symbol is a measurement. Together, the gate, Y, input and output mechanism implement quantum algorithm. Unlike classical circuit, which can contain loops, quantum circuits are one-shot circuit that just run once from left to right, which means each algorithm has its own specific quantum circuit. It should be noted that it is always possible to rearrange quantum circuits so that all the measurements are done at the end of the circuit. Quantum circuit diagrams have the following constraints which make them different from classical diagrams. The first is they are acyclic, which is no loop in the circuit. The second is no fan-in, as fan-in implies that the circuit is not reversible. The third is no fan-out, as we can copy a qubit state during the computational phase because of the no cloning theorem.
Here, why do we need a quantum computer? Let's talk about its history first. The idea of quantum computing was proposed by Richard Feynman. In 1982, the classic computation could be dramatically improved by quantum effects. Then, about 2 years later, David Deutsch developed the basis for quantum computing. And in 1994, a surprise by Peter Shor, he made Shor's algorithm that finds prime factors for a large number in polynomial time using quantum computing, and it completely shatters the RSA encryption. Then in 1996, Love Grover developed a fast database search known as Grover's algorithm. And finally, the first quantum computer 2-qubit has deployed in 1998 and followed by 3 and 7 qubit a few years later. Next, let's talk about what problem to solve with quantum computing. First, we have to understand the category of computation problem. The problems are classified by how many computation steps to solve a large example problem using the base known algorithm. First, P problem or polynomial, which is the problem that can already be solved in polynomial time. Second is the NP problem or non-deterministic polynomial problem. The solutions are easy to verify. However, some of the NP problems still doesn't have an algorithm to compute in polynomial step yet. And the last one for classical computing is NP complete, which has no known algorithm to solve this problem. However, if there are algorithms to solve this, it is likely to adapt the same algorithm to solve all this category of problems. And here's the special category for quantum computing: bounded error quantum polynomial time, or BQP problem. To state the problem that quantum algorithm can solve, it covers P problem, some of the NP problem. However, the NP complete are believed to be out of reach. Quantum computers seem to be able to solve some problem outside the NP area, which means quantum computer could solve some problem faster than classical computer can verify the answer. Computer scientists do know that BQP cannot extend outside the class known as P-space. P-space problems are those that a conventional computer can solve using only a polynomial amount of memory, but possibly requiring an exponential number of steps. For the implication and applications, quantum protocols. Application of quantum information processing include a number of communication and cryptographic protocols. The two most famous communication protocols are quantum teleportation and dense coding. Both use entanglement shared between the two parties that are communicating. First example, quantum key distribution protocol establishes a secret symmetric key between both parties. The security rests on properties of quantum mechanics. Or a symmetric key encryption scheme that guarantees that an eavesdropper cannot copy an encrypted message without being detected. Unclonable encryption has strong ties with quantum authentication. One type of authentication is digital signatures. Quantum digital signature schemes have been developed, but the keys can be used only a limited number of times. For broader implication, a quantum information theory is a mathematical theory of acquisition, storage, transmission, and processing of information, just like in classical but using quantum mechanics as a system to studies. The underlying quantum mechanics leads to some distinctively new features which has no classical counterpart. From this, we make use of the entangled state and quantum control to deal with matters that scale below the wavelength limit, or even use this knowledge to build extreme accurate sensor. Moreover, quantum information processing viewpoint has provided a new perspective about complexity and inspired classical computing a new algorithm from this new perspective. For example, lower bound for problems involving locally decodable codes, local search lattice, reversible circuit, and matrix rigidity. Next one is the impact on security. Cryptographic protocols usually rely on the empirical hardness of the problem for the security. Both factoring and the discrete logarithm problem candidate NP intermediate problem, and lattice-based problem are one of the leading candidates. However, similar problems to lattice are already been solved by Shor's algorithm, which makes many people nervous. Given the historic difficulty of creating practical public key encryption system based on the problem other than factoring or discrete logarithm, it is unclear which will come first, the large-scale quantum computer or practical public key encryption system secure against the quantum and classical attack. If the building of quantum computer win the race, the security of electronic commerce and communication around the world will be endangered.
Now let's talk about limitation of quantum computing. The limitation of quantum computing in providing speed up for certain type of problem. There is proof that for a broad class of problem, quantum computation cannot provide any speed up. This means that quantum computing cannot solve this problem faster than classical computing. Overall, the limitation of quantum computing in providing speed up for certain type of problem are still being explored, while quantum algorithm can perform select tasks more efficiently than classical algorithm. For many tasks, quantum algorithm provide no advantage. The breadth of quantum computing application is still being explored, with major application areas including security in fields that will benefit from efficient quantum simulation. The quantum information processing viewpoint provide insight into the classical algorithm issue as well as the deeper understanding of entanglement state and other non-classical aspects of quantum physics. From the potential limitation of quantum computer, why physicists should continue to work on building them, so it provides 4 reasons for why quantum computing is still important. The first is simulating quantum physics. If quantum computer become reality, the most important application is likely to be simulating quantum physics. This is a fundamental problem for fields such as chemistry and nanotechnology, and Nobel Prize have been awarded for this progress area. The second is relevant for classical computing. As transistors in microchip approach the atomic scale, ideas to create quantum computing are likely to become relevant for classical computing as well. The third is focusing on mystified features of quantum mechanics. Quantum computing experience focuses attention directly on the most mystified feature of quantum mechanics. By not ignoring the puzzle, we may be forced to understand them better through the experience on them. And the last is stringent test for quantum mechanics. Quantum computing can be seen as the most stringent test to which quantum mechanics itself has ever been subject. If quantum computers are not possible, it would overturn our current understanding of the physical world. If they are possible, it would merely confirm it.
For the summary, the scalable quantum computers are likely to success, but it will never replace the desktop computer. Quantum computer will always be harder to build and maintain than classical computers. So they will not be used for the many tasks that classical computers do equally efficiently. Quantum computers will be helpful for a number of specialized tasks. The extent of these tasks is still being explored. However long it takes to build a scalable quantum computer, and whatever the breadth of the application turns out to be, quantum information processing has changed forever the way in which quantum physics is taught and understood. The quantum information processing view of quantum mechanics clarifies key aspects of quantum mechanics, such as quantum measurement and entanglement state. The practical consequence of this increased understanding of nature are hard to predict, but they can hardly fail to profoundly affect technological and intellectual development in the upcoming era.
Thank you for watching.